Now we will prove a result in little L1, and this is a wonderful source of constructing counterexamples. Okay, so we have the following proposition. This is called Schur's lemma. Let xn be a sequence in L1. It is weakly convergent if and only if it converges in norm. So this is a remarkable result. So weakly convergent means convergent in the weak topology, and then it says there is no difference between the convergent sequences in the two topologies. Okay, so proof. So we know that norm convergence implies weak convergence. So we have to prove. So to prove weakly convergent implies norm convergent. Okay, so let us take, without loss of generality, let xn weakly converge to 0, because if it converges to anything else we can consider the difference xn minus x, so that will converge weakly to 0. So it is enough to converge. So to show norm xn goes to 0. Okay. Okay, so let us write xn equals xn 1, xn 2, xn I, and so on. So these are the coordinates. So fi is the ith coordinate projection, and that is a continuous linear functional, and therefore you have, so fi belongs to L1 star, and therefore you have that fi of xn goes to 0. That means, that is, limit xni as n tends to infinity equal to 0 for all n. Okay. So now assume, if possible, you have that xn does not converge to 0 in norm. Then there exists an epsilon positive and a subsequence such that for infinitely many n we have sigma k equals 1 to infinity x n k modulus, that is the L1 norm, is greater or equal to epsilon. So it has to be bounded away from a neighborhood. So you take a ball of radius epsilon near 0. The sequence does not converge to 0, means there are infinitely many outside. Thus we have a subsequence for which star holds. So we will henceforth work with the subsequence and so assume star holds for all n. Okay, because otherwise I'll have to put another index for the n, and there are too many indices, will be confusing. So we just work with the subsequence for which this is true, and then we will say, so given any sequence, so if we can prove that the subsequence goes to 0 in norm, then automatically every subsequence will have a further subsequence which goes to 0, and therefore the entire sequence will have to go to 0. So this is the standard method in topology, and therefore without loss of generality we can do this. So now we set n naught equals m naught equal to 1. For k bigger than 1, define nk and mk inductively as follows. So the first one, you take nk is the smallest positive integer strictly bigger than nk minus 1, such that sigma j equals 1 to m k minus 1 of x n k j is less than epsilon by 5. Why can you do this? Because we know every coordinate sequence converges to 0. And therefore here you have only a finite number of such sequences, coordinate sequences, namely j equals 1 to mk minus 1. So mk minus 1 is already determined, and therefore you have a finite number of them. So you can always find sufficiently large nk such that this is true for all j equals 1 to mk minus 1, and consequently, so since coordinate converge to 0. Okay. Now, having chosen nk, choose mk strictly bigger than mk minus 1, such smallest positive integer strictly bigger than mk minus 1, such that sigma j equals mk plus 1 to infinity mod x nkj is strictly less than epsilon by 5. Why is this possible? We have that x nk belongs to L1, therefore this is the tail of a convergent series, so you can always make it as small as you like. Okay, so now define y equals yj in L infinity as follows. So for mk minus 1 plus 1 less than or equal to j less than or equal to mk, you define yj equals 0 if x nkj equal to 0, otherwise it is a sign. So mod x nkj by x nkj otherwise. Okay, so mk is a subsequence which goes to infinity. Okay, so mk is strictly bigger than mk minus 1, and therefore it's a subsequence which goes to infinity, and starting from 1 of course, and therefore every j will fall in some such interval. So every j falls in some such interval, and therefore yj is defined. So yj defined for all j. So you are taking 1 to infinity, the integers, so you break them up as 1 equals m naught, then you have m1, then you have m2, mk, and so on. So in each interval you define yj. If j falls in any of these intervals, you define them, and therefore you have defined it for all j. Then clearly norm yj, norm y infinity is 1, because the supremum is just 1. So now you look at modulus sigma j equals 1 to infinity x nk j yj minus mod x nk. So I am going to take the modulus inside. So I get mod x nkj, mod yj will be less than or equal to 1, plus mod x nkj. So that will give me 2 times mod x nkj for j equals 1 to infinity. But I am going to split this sum j equals 1 to infinity as sigma j equals 1 to mk minus 1 plus 2 times sigma mod x nkj. Now from mk to mk minus 1 to mk, xj yj is 0. Okay, xj yj is mod x nkj minus mod x nkj, that gets 0. So this will only come from j equals mk plus 1 to infinity. So in between, in this particular interval, xj yj is equal to mod x nkj, and therefore it gets killed, and therefore it's now by our choice each one of these is less than epsilon by phi. So this is less than 4 epsilon by phi. So the two choices we have made here and here, that makes it less than 4 epsilon by phi. Consequently, by the triangle inequality, what do you get? Sigma j equals 1 to infinity xnk j yj is greater than or equal to sigma mod xnkj, and that one is bigger than epsilon, and this difference, which is 4 epsilon by 5, which is equal to epsilon by 5. Okay, so this, what does this mean? I have found yj, which is L1 star is L infinity, remember that. So yj, y belongs to L infinity, and I found xnkj yj bigger than or equal to xn phi, and therefore xnk fails to converge to 0 weakly, because it's bounded, this thing is a wave. But that's a contradiction, because you know that xn converges to 0 weakly, so any subsequence must also converge to the same limit weakly. So this proves the thing, and consequently you have established the thing. So what have we shown? So this is, as I said, has lot of applications and source of counterexamples. So the first immediate remark is the following. So L1 is an infinite dimensional space. Hence, norm and weak topologies are distinct. So weak topology is strictly contained in the norm topology. So there are norm open sets like the unit ball, open unit ball, which is not weakly open, and therefore these topologies are distinct. However, convergent sequences in both topologies are the same. So when studying topology, you would have seen that sequences are insufficient, and therefore people have made a lot of noises. That's why you study filters and nets and these things. Okay, so in metric spaces, if two metric spaces topologies have the same convergent sequences, then the two metric topologies are one and the same. However, in general topological spaces, this is not true, and here is an example. You have the norm topology, which is a metric topology, and the weak topology, which is different from that. They have the same convergent sequences, but the topology is not the same. So you cannot just work with sequences. So this is justification for studying nets and filters and so on. Okay. So this is the, we will have several occasions to use Schur's lemma to construct counterexamples or show examples for various things. Okay. So now we have a definition. VW Banach and T from V to W linear. So we say T is weakly continuous if T is continuous when both V and W are given their respective weak topologies. So you put the weak topology here in V, the weak topology in W, and then if T is a continuous mapping there, then you say that it is weakly continuous. Okay, so now we want to characterize this. So lemma. So VW Banach, T from V to W linear. Okay, then T is weakly continuous if and only if for every F in W star, F composed with T is weakly continuous. Okay. So F composed with T is a linear map from V into the scalar field R or C, whatever you have, let us say R, and therefore now weak topology in R, of course there is only one topology, namely the usual topology, which is both the weak and strong. For V, if you put the weak topology, then F composed with T into R, which is a linear functional, must be continuous with the weak topology in V. Okay, so then you say that characterizes the thing. Okay, so proof. Okay, so assume T is weakly continuous. Then clearly F composed with T is weakly continuous. Because what is the weak topology in W? It is the best smallest topology such that HF in W star is continuous. So every continuous linear functional is automatically weakly continuous, and therefore if you compose two weakly continuous mapping, you get weakly continuous. So this part is trivial. So now let F belong to W star, okay, and U open in R, of course, or C if you like, if you are working with complex spaces. Okay, then F inverse of U by definition is weakly open in W. Okay, and we are also given that F T composed with F, F composed with, weakly continuous implies T inverse F inverse U is weakly open in V. Okay. So T inverse, that is, but every weakly open set in W is nothing but is an arbitrary union of finite intersections of sets of the form F inverse U, and therefore you have T inverse of all these sets. So that means if you have V, sorry, not V. So if so U weakly open, not U again. So let me, I need a better symbol. So if A weakly open in W, then T inverse A is weakly open in V. So this implies T is weakly continuous. So this proves the particular lemma. Okay, so now we have the theorem that actually we don't have to make so much of a fuss because of the following theorem. So VW Banach T from V to W linear, then T belongs to LVW, that means it's a continuous linear transformation with the norm topology on both sides if and only if T is weakly continuous. So we made this definition and made some fuss, but actually usual continuity and weak continuity are one and the same for linear maps. Okay, so that is a very nice thing. So proof. Okay, so let us take T belong to L of VW. Then if F belongs to W star, then F composed with T belongs to V star, and this implies that F composed with T is weakly continuous, because every element of V star is automatically weakly continuous, and therefore by lemma T is weakly continuous. Now let us assume the converse, T is weakly continuous, and we want to show that T is L1. Okay, so then what does this mean? T is weakly continuous implies for every F in W star we have F composed with T is weakly continuous. But F composed with T is weakly continuous means what? F composed with T goes from V to R or C. Okay, and that means inverse image of every open set is weakly open. But weakly open topology is smaller than the norm topology, and therefore F composed with F T inverse of every open set is also norm open. Therefore implies is also norm continuous. So if it's continuous with respect to a poorer topology, it is going to be certainly continuous with respect to richer topology, because there are more open sets there, and therefore this is true. Then we saw this exercise, you know, that W star separates points and in W, and we used this and the closed graph theorem. We did an exercise in the last chapter, and therefore this implies that T belongs to LBW by the closed graph theorem, by an earlier exercise. We precisely showed that a linear map is continuous if F composed with T is continuous for all T F in W star. Okay, so this is exactly what we have. Okay, so then that proves this. Okay. So we now have as norm Banach space V. So you have two topologies here. We have the norm topology and we have the weak topology. So now if you have V star, which is also a Banach space, you will have the norm topology, you have the weak topology, and then we are going to define one more, which is called the weak star topology, and study its properties. So we will see that next time.